Welcome back. Welcome to the fourth part of our solution for the second homework. We are getting to the end now. And since the last two problems are quite similar to the ones that we have already solved, I will not be going into much of the details. I will just skip a couple of algebraic steps and leave them to you. And I hope that we can finish this quickly. Okay, in this problem again we will be using the method of images idea, and by using the image of this whole rod we will be evaluating a double integral to find the exact force between the rod and the infinite plane. You see, for infinite plane of this sort we have total charge of Q and L rod over here. Since this is grounded and the distance is D over here, we expect to see minus Q rods whose length is L as it is the image of the real charge. And under these circumstances, now in order to find the force between the two, realize the fact that I always need to, for instance, over this region, all of these rod effects on this region, and the same is valid over the whole region over here. So let me define two dummy variables. First is y1 dy1, and the second one is, let's say, y2 and dy2. Okay, and by taking integrations over y1 and y2 coordinates I can calculate the force between the two. However, while I am doing this, realize that this is the geometry that I need to work with, but since the overall force must be along this direction with respect to each other, so not only that I find this force, but also I need to make sure that I multiply it by the cosine theta, right? So df, let me call this z, is equal to df cosine theta, where df is nothing but dq1 dq2 divided by 4 pi e0 multiplied by 2d square plus y1 y2 minus y1 square. Okay, but what are dq1 and dy1? dq1 is nothing but q over l dy1, and dq2 is q over l dy2, right? Charge density multiplied by the total length of the region. So under these circumstances, let me also notice what cosine theta is. Cosine theta is 2d divided by what is it, 2d square plus y2 minus y1 square to the power of 1 over 2, which means that in overall dfz is equal to dy1 dy2 q over l square, right, 2d over 4 pi e0 multiplied by 1 over y2 minus y1 square plus 2d square to the power of 3 over 2. Okay, let me quickly check. Yes, 2d q over l squared, etc. And so overall, what is fz then? From minus L2 plus L2, from minus L2 plus L2, dy1 and dy2, right? And then dfz. Yeah, sorry. dfz was already including dy1 and dy2, and the Rest Q over L square 2D over 4 pi E0 1 over y2 minus y1 square plus 2D square 3 over 2. Okay, let's proceed further. It is equal to Q over L square. Let me be quick about it. D over 2 pi E0. You can check the algebra by yourself. Plus L over 2 dy1 dy2 y2 minus y1 square plus 2d square 3 over 2. Now I need to take this integration. The first step goes as follows. Let me call this whole a constant c multiplied by minus L over 2 plus L over 2 dy2, right? y1 minus y2 divided by y1 minus y2 square plus 2d square over 1 over 2, where we need to evaluate the whole integral for y1 from minus L over 2 plus L over 2 multiplied by 1 2d square. This is coming from the integration. And further, it is now equal to 2d square from minus L over 2 to plus L over 2 dy2 L over 2 minus y2 and L over 2 minus y2 square. This has a very long algebraic work. 1 over 2 minus L over 2 minus y2 divided by minus L over 2 minus y2 square plus 2d square 1 over 2. Okay, let's define du to be minus 2 L over 2 minus y2 dy2 and dv to be 2 L over 2 plus y over 2, sorry, y2. Let me check, y2 dy2. Okay, and by using these, at the end you shall end up with the following: c over 2d square L square plus 2d square minus 2d, which means that f is nothing but q over L square 1 over 2 pi E0 4d multiplied by L square plus 4d square minus 2d. Okay. Okay, we would like to analyze what happens if D is much larger than L. What is going on physically? So the rod is quite away from the infinite plane with respect to its dimension. In this case, we would like to re-express in terms of L over D, right? To do this, F shall be equal to Q over L square 1 over 8 pi E0D in 2D parentheses, 2D over here, 1 plus L over 2D square minus 1. Okay, so Q over L square 1 over 4 pi E0, right, multiplied by, expand this, 1 plus 1 over 2 L over 2D square minus 1. right? Okay, these shall cancel, else shall cancel, and I end up with Q divided by 8 pi E0 2D square as my answer, Q square, which acts like 2-point charges, and that is the intuitive expectation. By the way, then it needs to be 4 over here. It should be 4. But why I then ended up with 8, I couldn't figure out for the moment. It should be 4. 1 plus 1 over 2 L over 2D square. Let me quickly check. This is 1, yes, 1 plus 1 over 2, 2D square. I couldn't. Let me see it again. I don't know, I have forgotten some 2 somewhere, someplace. Anyway, that was the whole idea. Okay, what about the C part of this problem? This is the B part. On the C part of the problem, we would like to see the surface charge density, and surface charge density in this case can be expressed as 2E0 E perpendicular to the surface, and E perpendicular to the surface can be found out by again the very same integration or the potential, etc. I will not go over it here. I will just write down the equation. We have already done the similar calculations. Q over L D 2 pi x square d square multiplied by L over 2 minus y divided by L over 2 minus y square plus x square d square minus L over 2 plus y divided by L over 2 plus y square plus x square plus d square. Okay. This you can do it by yourself as an exercise, because it has again very long algebraic practice. Find the total charge induced on the plane without integrating sigma xy. The induced charge is nothing but minus q expectedly, because it is coming from the fact that in reality this charge distribution over here and L, right? And this simply attracts the minus side to the right side of the surface. Right side of the surface. Hence, why is it minus q? Because you see it's a thin, quite a small thickness, but it has still like thickness, and it's a conductor, and by theory there does not exist any E field inside the conductor. Otherwise, if there exists anything during a transient phenomena, the electrons are quite free to arrange themselves that so they move until there is no E field inside the metal. Hence, there does not exist any E field conductor inside the conductor. Hence, to achieve this, minus q amount of charge is induced onto the right side of the infinite plane. Because once you draw a Gaussian surface that passes through just below the just behind side of the right side of the surface, I need to end up with a zero E field, and in order to achieve that, the Q enclosed must be 0, and I am enclosing Q over here, so minus Q must be induced. Even though this geometry is not quite easy to imagine, let me explain this through a spherical surface. Once I have this sort of geometry, I induced minus charges over here. The amount of the induced charge, the overall must be minus Q, because once I draw my Gaussian surface over here, the enclosed charge must be 0. Q enclosed must be 0 to make sure that E field inside the hollow conductor is 0. That's the idea. Hence, in this case, plus Q is at the outer surface of the overall conductor. Okay. Let me pass to the very last problem now. In this problem, again, I will quickly go over it. On the 7th problem, again, it's a boundary green function problem, but this problem now requires the following. Again, I need to be satisfying these. Right? And G at R equals to RS, R prime is equal to 0. That was the whole idea. But in this geometry now we have a cylindrical symmetry, but we also have some finiteness along the Z direction. Okay. And furthermore, it has the phi 0, phi 2 pi over P conditions, and then Z equals 0 and Z equals to H conditions. Okay. To satisfy these conditions, the Z part of the green function are just defined as Z prime sine, very similar idea, m pi Z over H multiplied by sine m pi Z prime over H. Similarly for phi prime sine m pi phi divided by 2 pi over P sine m pi phi prime divided by 2 pi over P. These can be evaluated so that G R at RS R prime is equal to 0 at the given surfaces. So let me re-express the phi over here. Phi sine MP phi over 2 multiplied by sine MP phi prime over 2. That is in this form. Now, given these, what is the function of G now? G rho phi Z rho prime phi prime and Z prime is equal to mn. By the way, one of them shall be n over here. Okay, n, right? GMN rho prime multiplied by all of these functions. Sine m pi what was it? Yes, m pi z over h, sine m pi z prime over h multiplied by sine n pi phi over 2 sine m pi phi prime over 2. This is the whole expression for G. We are not done yet, of course. We also need to satisfy this boundary condition. This differential equation is equal to minus delta r minus r prime divided by E0. And in this case, it is now equal to minus rho z minus z prime, rho minus rho prime, phi minus phi prime divided by rho E0. Apply the very same procedure from the previous problem, from the question 4. We end up with the following differential equation. E0 multiplied by 1 over rho d over d rho d g mn d rho minus mp over h square plus mp over 2 square 1 over rho square gmn is equal to 1 over minus 1 over rho delta rho minus rho prime. Okay. This is the differential equation that we need to solve. I know not to solve it. Of course, it's quite long to be done. But instead of solving this, I will just be writing down the boundary conditions must be satisfied by the above equation. Which is, as rho smaller than rho prime, gm rho goes to 0, rho prime must go 0. Rho greater than rho prime, gmn, as rho goes to infinity, rho prime must go to 0. That was the other equation, boundary conditions that we need to satisfy. Furthermore, at rho equals to rho prime, we also need to satisfy the following: dgmn over d rho at minus dgmn divided by d rho minus e must be equal to what? This shall cancel. Minus 1 over rho prime E0. There can be another term that we need to add here. I need to check it. Let me quickly check. Yes, there exists a term of 2 pi over pH. Okay, coming from the derivation term. Okay, hence 2 pi over 2p over pH must be added to. Under these conditions now gmn can be found. Okay, I will not go into the rest. This is the last boundary condition that we need to satisfy. The rest we have already done a similar process on the previous example. Okay, thanks for your patience. This is the end of the recitation. I would welcome any sort of questions, including on an email or in a comment, etc. And furthermore, until the exam, if there exists any other form of question that you want me to solve, I can also try to